To power a modern city, you have to feed a massive, relentless machine. Every day, millions of gigawatts of electricity course through grids of concrete and steel, just to keep the lights on, the servers running, and the trains moving. And right now, we urgently need to decarbonize all of it. The standard tool for that job is the silicone solar panel. But silicone has strict physical limits. It requires heavy glass casings and thick metal frames to protect the brittle wafers inside, making the panels rigid, bulky, and difficult to install. Because you cannot easily bolt hundreds of pounds of glass onto older roofs or vertical walls, solar farms are forced out into vast, flat landscapes. For geographically constrained nations like Japan, where cities are packed tight against unbuildable mountainous terrain, we are simply running out of empty land. To achieve carbon neutrality, we have to generate power everywhere. We need to turn the surfaces we already have into energy generators. But we cannot reach that goal if the technology requires strapping heavy glass to every building. In 2009, researchers in Japan developed a completely different approach to the problem. They created the Perovskite solar cell. Instead of rigid slabs, this is an ultra-thin film. It operates at 1/100th the thickness of standard silicon, weighs about 1/10 as much, and bends without breaking. Stripping away that dead weight allows every existing bridge, warehouse, and skyscraper to serve a double purpose: infrastructure that simultaneously functions as a massive distributed power plant. To understand how something this thin actually generates electricity, we have to zoom down to the atomic level. Perovskite refers to a specific crystalline structure, rather than a single raw mineral. This diagram shows that arrangement. In chemistry, it's called an ABX3 crystal structure. It forms a highly ordered repeating lattice, a cube with a smaller, 8-sided shape nested perfectly inside it. We can fill these geometric slots with different materials. Typically, the nodes hold organic compounds, a metal like lead or tin, and a halogen, most commonly iodine. Because Japan naturally produces about 30% of the global iodine supply, utilizing this specific chemistry offers a major advantage for their domestic energy security. To make a solar cell, this perovskite crystal is sandwiched between 4 other layers. You have a transparent electrode on top, an electron transport layer, the perovskite layer in the middle, a hole transport layer, and a back electrode. The entire stack is less than a micron thick. When sunlight strikes that ultra-thin middle layer, the crystal absorbs the energy. This excites the electrons, which carry a negative charge, knocking them out of position and leaving behind structural gaps, or holes, which carry a positive charge. In an instant, the transport layers above and below the perovskite pull those opposite charges apart. The electrons get pulled one way, the holes get pulled the other, and that organized flow of charge generates an electrical current. Because the distance these charges have to travel is incredibly short, almost no energy is lost in transit. It takes very little incoming light to trigger this process, meaning the cell keeps generating power even under heavy clouds or indoor office lighting. Because these materials capture and convert light across such a microscopic distance, the heavy physical bulk of a silicon wafer becomes redundant. That physical difference rewrites how we manufacture solar panels. Purifying silicon to a semiconductor grade requires massive industrial foundries and temperatures over 1,000 degrees Celsius. The raw chemical components of a perovskite crystal, on the other hand, can be entirely dissolved into a liquid solvent. This diagram illustrates how we can take that liquid solar ink and run it through a standard roll-to-roll printing press. It continuously coats long sheets of flexible plastic at around 100 degrees Celsius. Lowering the heat requirements cuts the energy consumed during manufacturing. It reduces the need for expensive, specialized facilities and allows the panels to be printed at extremely high speeds. When you can print a solar panel the way you print a newspaper, you remove the industrial bottlenecks that have kept production costs high and deployment slow. Once this printable film leaves the factory, it changes the logistics of how and where we deploy the electrical grid. Think about the massive distribution warehouses and older factories sitting in industrial parks. Many of them have strict roof weight limits that make installing traditional solar panels structurally impossible. Perovskite film can simply be rolled out over those vulnerable roofs, turning dormant surfaces into active power generators. We can also integrate it directly into the architecture. By tweaking the chemistry, perovskite materials can be made semi-transparent. This allows engineers to sandwich the film between standard window panes. Entire vertical glass facades generate megawatt power without blocking the view from the inside. The applications extend beyond buildings. You can paste this film onto the curved roofs of electric vehicles to charge the battery while driving. You can even use it to power small smart sensors and IoT devices, running entirely off the ambient glow of indoor lighting. By solving the problems of weight, rigidity, and low light performance, we've broken the rules of traditional solar. The physical shape of a power plant no longer limits where it can exist. To scale this globally, researchers still have to clear a few engineering hurdles. They are working to improve the film's long-term durability against moisture and to mitigate environmental concerns surrounding the lead content used in high-efficiency cells. But the timeline is accelerating. This technology is crossing the threshold from laboratory prototypes to commercial realities and public exhibitions slated for 2025. We are moving away from the search for empty land to build miles of solar farms. As we integrate the perovskite crystal into our urban fabric, the cities of tomorrow will evolve into vast, self-sustaining generators of their own energy.